So in the second day of diffraction and Young's double slit experiment, we're going to first start off with a little bit of an experiment. So I'd like you to go to your site and print off the 2 PDFs I have for day 2. So first what I want you to do is you're going to cut out the individual waves of wave, and each wavelength should be 1.5. So that should be a PDF with these little waves like that. Next, you're going to use these waves to decide if a point will be constructive interference, which is bright fringes, or destructive interference, which is dark fringes. So remember, bright fringes are called antinodes and dark fringes are nodes. Or if they're going to be something in between. I want you to be ready to justify which one is which and why later on. So let's look at the mathematics of Young's little experiment here. So here we have our screen. We have our brightest antinode, which is our central node, and then we have our other constructive interference antinodes, which, as we notice, get darker as we move away from our central antinode. In between here, these are our nodes, and they are the dark ones. Okay? So, if we look at this here, we have 2 slits with a distance apart. Their wavelength, this one has 10 wavelength, this one here has 9 wavelengths to this node. So that is a difference of 1. So the light coming from slit 1 completes 10 wavelengths, and the light coming from slit 2 completes 9 wavelengths. This should produce constructive interference. So now here is my next question, and I want you to think about this. What would produce destructive interference? So what would maybe these 2 wavelengths be to get the first destructive interference? Now remember from the lesson before, to get destructive interference, we need a difference of half a wavelength. Let's see if you can figure out which ones those are. Now, how do we make this equation? So mathematically, we looked at some things, but we're not 100% sure how to calculate where each point will be. Well, this is how we're going to do it. I know you're thinking about it, but it's not as, and it's a little bit easier than you think. So first what we're going to do is we draw a perpendicular line from S2 to S1P, okay? From slit 2 to slit 1 to our first point, which is our node. Then what we're going to do, second, is we now know that PW, okay, so PW, this right here, PW is equal to PS2. So these 2 lines here are the exact same length, okay? And we also know then that WS1, so we know W to S1 is our path difference between them. Because if this line is equivalent to this line, then this line here is our path difference between them. And that is essentially what we want to find to figure out if we're going to be in a node or antinode, is that path difference. If it's a whole number, it's an antinode. If it's a half number, it is going to be a node. And then everything else is going to be kind of in between. So now once we know, most of the time we'll know the difference between the slits, and all then we need to do is find out this angle. So let's build this equation here. So we have sine theta n is equal to the difference in path length divided by my difference in slits. So for constructive interference or antinodal lines, we substitute generalization for the difference in path lengths of above. Okay? So we say n will give us our angle. So this could even help us find my angle. Or in other words, if we're trying to find that wavelength difference, all we're just going to say is we have my distance and slit, and we know the angle, then we could divide it by which node we're trying to find. So N1, 2, 3, 4, and so on. So remember, at the central node, they should be the same anyway. That's why we don't have 0 there. So here's the picture we have been working with. Now, here's the thing. From our bisector, from the center to our bisector, this angle here is essentially the exact same as this angle here, from S2 to X, making this triangle. These are equal. They are called the angles of diffraction. So when we're talking about the angle of diffraction, it is the angle from my center to the node from the bisector right here, which will be equal to this angle right here, if we make this little triangle to try and figure everything out. And C is the midpoint. So, destructive interference. Well, destructive interference is halfway between nodes. So in other words, all we have to do is we take our node and we're going to minus 1/2 to figure out each level of destructive interference. My first node, my second node, and my third node. So we're just taking our antinode and we're minusing 1/2 to get my actual node. Okay? So this is to find my angle, and here will be to find my wavelength. So this is my angle of diffraction, okay? And this one here is my wavelength. So here is my first example. We have a monochromatic light is incident on two slits separated by 0.3 millimeters. And the first bright fringe is one antinode. Is located at an angle of 0.08 degrees from the central antinode. What is the wavelength of the light? So here we know my angle of diffraction is 0.080 degrees. We know my distance between slits is 3 times 10 to the negative 4 meters. And I know my node that we're trying to figure out is the first one. So now we're going to plug that all into our equation. So we're trying to find my wavelength. So we are going to use this equation here, and then we plug in everything here. So we know my distance is this, I know my angle is that, and my node is 1. So I multiply these together, and the only units we have is meters, so I'm going to get a wavelength of 4.2 times 10 to the negative 7 meters, and that will help us even find my wavelength. So here are 3 problems for you guys to practice on your own.